So here I'm going to go ahead and walk through your Peardeck with you because these are atomic structure notes that I would typically go through in class. And when you first look at the presentation, you're going to possibly notice that it's a lot of slides. But the first half of the presentation is just a review of the stuff that you've already covered. So you already covered atomic theory. You can go through those slides fairly quickly, but those of you who need some more reinforcement on the material or need to take more formal notes, I've gone ahead and given you those notes, and that way you can kind of go back to those notes for future reference, especially when you're studying for your tests and whatnot. So I'm going to go ahead and answer my question, how am I feeling today? And we are going to get moving with our atomic structure notes. So this is Unit 3, and it's covered in CK12, Chapter 2. And then I'm going to go ahead and put this link to the screencast of these notes right here for you. So what I want you to do is I want you to go ahead and answer this question. There are two bottles on a shelf in a chemistry lab. Both contain a shiny metal substance that resembles gold. Bottle A is labeled AU. Bottle B is labeled FES2. Do you think both bottles contain gold? Why or why not? And what do you think the symbols are in the bottles, the symbols mean? So you're going to go ahead and type your answer, okay? Obviously, I want you to go ahead and write an actual answer for me. I do check those answers as we're going through. And then we're going to go ahead and move on. So a little bit of a review, and I'm going to go through these first few slides very quickly because we've already gone through them. But an element is going to be your smallest piece of matter that's not going to be able to be decomposed by a chemical reaction. It's the most simple substance, and it's the most unique. The smallest unit of an element is an atom, and that's what we're going to be studying in this unit is atomic structure and atoms. Now, compounds are composed of two or more elements that are chemically combined. You're going to write a chemical compound as a formula, and the smallest unit of a compound is going to be either a molecule or a formula unit. So the chemical formula, when you look at these symbols here, you're going to notice we have NaOH, NaNO3, CuSO4, CaOH2. Now, those are basically telling you, it's like translating. You're going to be translating into a different language. So you're going to be translating into science language or chemistry language. So this is sodium hydroxide, sodium nitrate, copper 2 sulfate, and calcium hydroxide. Now, you're not going to be doing this until the very end of this quarter and then moving into second quarter. But I do want you to be familiar with the fact that those symbols actually mean something. But the question at hand is how many of each element are in each of the above. So here I have one Na, I have one O, and one H. One Na, one N, 3 oxygens, because that 3 goes with just the oxygen, 1 Cu, 1 S, and 4 oxygens. Now, someone might ask, how do you know that that's Cu together? And it's because I have an uppercase and a lowercase. So every new uppercase starts a new element. So here I have 1 Ca, and then I have 2 OHs. So I have 2 O's and I have 2 H's. So this is kind of using the distributive property in math. It's going to be the same thing. So again, 1 Ca, 2 O's, and 2 H's. Now, how many elements are there in total of each of the above? So I can go ahead and add how many elements total there are. And that would actually be how many atoms. That should say how many atoms are there in total, not elements. Because if I was looking at elements, it would be 3 elements. This would be 3 different elements. And this would be 6 elements. And this right here is going to end up being this is going to end up being 3 different elements. So this is 3 different elements. But atoms total would be 6 and 5. And I'll go ahead and change that before you actually see this presentation. And then symbols, your first letter is capitalized, and second and third letters would be lowercase. So now you try. How many of each element are there in that compound? And then how many elements are there in total? And I will change that to be total atoms in one compound there. So go ahead and write your answer there. And for these, go ahead and do A and then B, and then give me your answers there before you move on. So looking at atoms, atoms are the smallest part of matter. So if you were to take some aluminum foil and you were to tear it, so imagine I'm standing in front of you and I have a piece of aluminum foil and I tear it in half. I still have aluminum. And I tear it in half again. I still have aluminum. I tear it in half again. I still have aluminum. And one of the videos that you actually watched had something to do with if I were to break wood down into the smallest piece, I still have wood. And within every piece of dust, of wood dust, I have many different atoms. Okay, and so all matter is made up of particles that cannot be divided, and those are called atoms. So the word atoms comes from atomos, which means indivisible. Atoms means comes from atomos, which means indivisible. So atoms are made up of protons, neutrons, and electrons. So eventually, scientists over time, and we're going to look at the different models, over time, they realize that atoms are actually made up of smaller particles. Now, you no longer have the same chemical properties of the atom that you had, but you still have a certain number of electrons, protons, and neutrons. And those are kind of like the DNA of the atom, is the protons, the neutrons, and the electrons. Electrons have a negative charge, protons have a positive, and neutrons are neutral or have no charge. Protons and neutrons are in the nucleus. Atoms are also microscopic, and they're the building blocks of matter. So these next few slides are going to strictly review what you covered in the last couple of days. So early philosophers believed that all matter, everything was made up of earth, water, air, and fire, and that everything was endlessly divisible. So I could divide it and divide it and divide it, and there would be no breaking point, no end point. But then along came Democritus, who worked under Aristotle. And in 4th century BC, Democritus said, no, I really believe that there is something more. And so the Greek word atomos means indivisible. The problem with Democritus is that everyone kind of went with the early philosophers and didn't necessarily believe him for a long time, because Democritus, this was just a thought experiment for him. It had no backing of a scientific investigation or experimentation. But then along came Dalton, and Dalton was able to do some scientific research. And in the early 1800s, he was the first to verify that an atom is present, and that he was the first to verify based on experimentation. Dalton came up with his principles, and Dalton said all elements are composed of tiny indivisible particles. Atoms of the same element are identical to all atoms of that same element. Atoms cannot be divided, created, or destroyed. Atoms of different elements can chemically combine to form compounds, and chemical reactions occur when atoms are separated or joined. Atoms of one element will never change as a result of a chemical reaction. Now, since Dalton, our atomic theory and structure has changed, and I really liked the crash course that you watched that talked about how that has changed since Dalton. But it's really important to understand that Dalton is really the father of atomic theory. So along came J.J. Thomson, and J.J. Thomson discovered that there had to have been a negative charge. There had to have been something smaller than an atom. So J.J. Thomson is credited with understanding the charge to mass ratio of electrons, and he shot these cathode rays through this tube. And when he ended up seeing the deflection, then he ended up recognizing, okay, if it's deflected by the negative side, then this must be a negative charged particle in here. So a really interesting thing would be this cathode tube experiment. If you'd like to click on this link, And then you can watch a quick little video if you're not understanding what a cathode ray tube is. But J.J. Thomson was credited with the discovery of the electron. And then in the end, he came up with what was called the plum pudding model. And that was something that has been in your notes, and it's not in the next slide. So it's important for you to understand J.J. Thomson believed that an atom was made up of positive goop, and then there were all of these sprinkles of negative charges. So he called it plum pudding just because of historically the time, and plum pudding was very popular. Whereas nowadays you would almost think of it like a chocolate chip ice cream, where the chocolate chips are going to be your negative charges and your ice cream is going to be your positive goop. Or you could look at it like a chocolate chip cookie. Your cookie is your positive goop and your chocolate chips are your negative electrons. So some things that are very important for you to know about electrons and charge. Electrons are smaller than an atom, they're negatively charged, and they relatively have no mass, relatively speaking, compared to protons and neutrons. So all of the mass from the atom actually comes from protons and neutrons. Also, electrons can easily be removed, and hopefully we will do this in a demonstration where I will show you the easily removed electrons in a demonstration during our Zoom meetings this week. Now, electrons, something to note about charge is that opposite charges are going to attract each other, and like charges are going to repel. So negative charges will push away from negative charges, and positive charges will push away from positive charges. Also, something that's important to know is that the closer the charges are to each other, the stronger the forces are between those charges. And that's a really important physics concept, but it's going to blend itself into chemistry quite a bit. And atoms behave certain ways because of that concept, the fact that the closer the charges are, the stronger the force is. So then along came Millikan, and Millikan is credited with the oil drop experiment, and he basically was able to find the charge of an electron. So basically, he found that the charge of an electron is equivalent but opposite in charge to the proton. So, or to that positive charge. So the electron has a -1 charge, and protons, eventually we learned, has +1 charge. Now, something else that's important to recognize is that one proton has a mass of 1 AMU, one neutron has a mass of 1 AMU, but an electron basically has no mass. We consider it to be 0 AMU because, relatively speaking, an electron has a much smaller mass. So AMU, you might think, what the heck is an AMU? I've never seen that before. So because protons are so small and neutrons are so small, you're talking times 10 to the -19 kilograms, something like crazy like that. So scientists needed to come up with something that was more manageable to deal with on an everyday, all of the time basis. So 1 AMU is 1 atomic mass unit. Now, Rutherford is my favorite in atomic theory. So I'm going to really ask you who Rutherford is and what he did. So he's credited with the gold foil experiment. And this is really the foundation of like great scientific investigation. So you can go ahead and watch this quick little video right here. Each of these videos are about 2 minutes long. But Rutherford, what he did is he shot a laser through pieces of gold foil. And what really surprised him, he really expected everything to bounce back, but what really surprised him is that most of the rays ended up going through, the alpha particles ended up going through the gold foil. So that showed him that an atom was made up of mostly empty space. This right here, an atom is made up of mostly empty space, is super important. But because some of those alpha particles were deflected, it was important to note that because the alpha particles were positive, the center had to have something positive in it, but there had to be a center. So the nucleus was in the center of the atom. So Rutherford is credited with discovering that the atom is made up of mostly empty space, and also credited with the discovery of the nucleus, that there's something small in the nucleus. Now, something I hope you remember from the videos that you've watched is that the size of a nucleus and the size of an atom, when we talk about mostly empty space, we're talking like put a marble in the center of a football field. And that's the size of the nucleus, and all of the electrons are the fans that are in the stands. So that's how much empty space there is in an atom. I mean, it's gigantically huge. But understand that atoms are so infinitesimally small. And so it's not something we can see. And it's so hard to kind of imagine and picture. But it's true, and it's scientifically proven. So Rutherford, again, gold foil experiment, credited with the discovery that the atom is made up of mostly empty space and the nucleus is at the center of the atom. And that's where most of the mass is in the atom. So then Bohr comes along. Well, Bohr has changed things a little bit because now, instead of just believing that electrons are just kind of floating out there, Bohr predicts that that the electrons are circling, and we call this the planetary model. And it's because we kind of say that those electrons are kind of circling or orbiting that nucleus, kind of like the planets orbit the sun. Now, we've since learned that that's not true, but the most important thing with Bohr is that Bohr recognized that the farther electrons get away from the nucleus, the more energy they have. And electrons can jump from one energy level to the next. And that's going to be really important when we look at the periodic table and at atomic behavior. So Bohr is credited with the discovery of these orbitals, and the orbitals are energy levels. So you have your lowest energy level and closer to the nucleus, then you have higher, and then higher and higher. And electrons, as they enter energy levels, they enter from the lowest, moving all the way up to the highest. So when we're drawing Bohr models, and this is something that you probably learned when you were in junior high, but we're also going to look at this today a little bit. So when you're drawing Bohr models, you're going to put your protons and your neutrons in the center. Now, a diagram that you may have seen before would definitely be something like you have like circles. So like 3 purple circles and 4 orange circles or something. So how do we know what goes in the center? Well, we need to figure out how many protons there are and how many neutrons, and we're going to talk about that in the slides to come. But if I gave you something like lithium has 3 protons, 4 neutrons, and 3 electrons, place them. Well, it's important for you to see that your first 2 electrons go in your first energy level, but the maximum of electrons that you can have in that energy level is 2. So then you jump to the next one until you have used up all of your electrons. So we have 2 electrons in our first orbital, our first ring, and then we add 1 more electron in our next ring. So what I'd like for you to do is I'd like for you to draw draw one, okay? So now I have carbon, and I have 6 protons, 6 neutrons, and 6 electrons. So think about it. Where do the protons and the neutrons go, and then where do the electrons go? And then think about going back to your maximum number of electrons in your first energy level is 2, and then your next one is 8. So I intentionally made it so that you only have 2 energy levels, but go ahead and draw what this would look like. You can choose any colors that you want, and you can choose any kind of ink that you would like, okay? But go ahead and draw that and then submit that for me. And then finally, Schrodinger. Schrodinger is the quantum mechanical model. And basically, Schrodinger came out and said after Bohr, so Bohr, we have the planetary model, and Schrodinger was like, whoa, wait a second. Actually, I think that there's about a 90% probability of being able to find the electrons, and those electrons are in clouds. So rather than orbiting like a planet orbits the sun, you're going to end up having your electrons hang out in clouds, kind of like electron neighborhoods. So like there are different neighborhoods around Santana High School. And so you might have, you and your friends, your electrons are hanging out in one neighborhood, and then someone else might live like 2 miles away from the school and be hanging out in a different neighborhood. And it takes more energy to get to that second neighborhood. So Schrodinger came up with this idea of electron clouds and how the electrons behave in those clouds, and then how they can transfer and where they fill, basically. And what this actually ended up giving us, it ended up giving us an understanding of kind of magnetic properties, is kind of where Schrodinger goes. We won't spend very much time talking about Schrodinger, but it's this idea that electrons are not just orbiting the nucleus, but they're kind of moving around in these cloud structures, these orbitals. And the maximum number of electrons that can be in those clouds are 2 per cloud, basically. And we will maybe address that a little bit later. So some other important scientists, Goldstein is credited with the discovery of the proton, and Chadwick is credited with the discovery of the neutron in 1932. So that's the end of the atomic theory. So what I'd like for you to do is draw the progression of how has atomic theory changed over time. So you've got different people. How did it change from early philosophers all the way until basically we ended up getting to Schrodinger? So go ahead and draw that and submit it. Now, atomic structure, this is really the meat and the potatoes and the new stuff of what we're talking about. So we know that atoms are made up of protons, neutrons, and electrons, thanks to all of these people who have added to the scientific discoveries. And understand, I really want you to understand that there are so many other scientists in history that have helped in the discovery of these subatomic particles. And that's important to me to state, because I just want you to understand that there are lots of people who go into these discoveries and who are working in the labs with these people. It's not just a one person thing where one person discovers something. A lot of people are working together in teams, and that's how science is today. So three main components or parts of the atom are the electrons, the protons, and the neutrons. The protons and neutrons are in the nucleus, which is the center of the atom, and then the electrons are on the outside. It's also important for you to know that protons have a positive charge, neutrons are neutral, they have no charge, and electrons are negative. So what determines what? Well, it's important for you to realize that protons are going to determine the identity of the atom, and we figure out the number of protons from the atomic number or from the position on the periodic table. So no two different atoms are going to have the same number of protons. So for example, if I have carbon and oxygen, carbon has 6 protons, but oxygen has 8. If I said that oxygen had 6 protons, it's no longer oxygen. Oxygen is now, because it's become 6 protons, it's now become carbon. That's changing the nucleus of the atom. The electrons determine the charge of the atom. So a charged atom or a charged particle is called an ion, and we figure out the charge by figuring out protons minus electrons. And the reason it's minus electrons is because electrons are negatively charged. And then neutrons are figured out by the mass number. The mass number is the number of protons plus the number of neutrons. So when I'm looking at a square on the periodic table, you're going to have some kind of whole number, you're going to have a symbol, you're going to have a chemical name, and then you're going to have some decimal number. The decimal number is something that we're going to talk about in our next set of lessons, and that's going to be your atomic weight. But your symbol is this right here, your letters. It's almost like your initials. And your chemical name is going to be right here, the full name. And this number right here tells you how many protons there are. So that number tells you the identity and the position on the periodic table. So here's a practice problem for you. How many protons does oxygen have? So if I looked at oxygen on my periodic table, you see that there's an 8 right here. So oxygen has 8 protons because of that 8 atomic number. So oxygen has 8 protons. Now, how many electrons does a neutral atom of oxygen have? Well, if it's neutral, I have 8 positive charges, and so therefore I must have 8 negative charges. So I have 8 electrons. And then how many neutrons does oxygen have if it has a mass number of 16? So the mass number of 16 is something that I will give you in these practice problems, or I would give you protons and neutrons, and then you would have to find the mass number. So remember, mass number is protons plus neutrons. So I take my mass number minus my number of protons, and that gives me 8 neutrons. So go ahead and you try this. So finding potassium, and I circled that right here for you. Potassium is number 19. How many protons does it have? Now, if it was neutral, how many electrons does it have? And then here's an extra bonus question that's kind of interesting, is what if the charge was a positive 1 charge? So potassium, K, tends to form a positive 1 charge. Why is that? What happens? And no, this is something really important. understand that you can only change the number of electrons to change the charge. Because again, if you change the protons, you're changing the identity of the atom. So here's another practice problem of drawing an atom. So I'd like for you to look at, and I've already drawn this for you right here, but I want you to tell me, how many protons do you see? Okay, how many positives? How many neutrons are neutral charges, and how many negative charges? And what is the mass or the mass number on this atom? Okay. The weight of an atom is all in its nucleus, and the mass number is for one individual atom. And we consider protons to have a mass number of 1 and neutrons to have a mass number of 1. So valency and shells. So valence electrons are the electrons on the outermost shell. And what's going to be very important with valence electrons is valence electrons are going to tell us how many electrons are going to be able to be available for reactivity. So the valence electrons are really what determine the reactivity of an atom. Each atom has a number of electrons, but we want to really know how many electrons are in the outside shell. Now, it is important for you to see that the first shell can only hold 2, and then as you get up to 20, you actually go 8, 8, and then 8. And that's just because we're going down in rows on the periodic table. So that's just for when you're drawing, you're looking at valence electrons, and this is something that we will revisit in our next unit. So looking at the periodic table, atomic number is the number of protons. That's something that's really important for you to know. When you look at the periodic table, that number is the number of protons and the atomic number, and it tells you the position on the periodic table. Each successive element, meaning each element one right after the next, has one more proton than the element before it. The number of electrons is equal to the number of protons if it is neutral, only if it is neutral. And a little hint for you, valence electrons are what's really going to determine what charge is going to be formed on an atom. And we'll talk about that eventually. So mass number. Mass number is the number of protons plus the number of neutrons. And then you're going to look at atomic mass units. And this is really going into our next unit, or our next lesson. But atomic mass unit is the weight or the mass of a single atom, whereas the atomic mass is the weighted average mass of isotopes. And we're going to be talking about atomic mass quite a bit in our next lesson. And the reason for that is because atomic mass units is this invented number. And you're basically saying, okay, what is the mass of this one individual atom? Well, it's impossible to just pull out one individual atom at a time. So an atomic mass unit is actually relative to the mass of one carbon-12 atom. And we figure out, this kind of goes into the why electrons are 0, because the mass of protons is 1.67 times 10 to the negative 24 grams. So sorry, I said negative 19, but here it's 1.67 times 10 to the negative 24 grams. Neutrons are the same. So you see that you can set that equal to 1 because they are 1 relative to each other. But this mass of an electron times 10 to the negative 28, that's such a small number. So that becomes a mass of 0. Okay, and so we're going to figure out the atomic mass units based on isotopes. So what is an isotope? Well, each element, and this goes back to Dalton. Dalton said that every single atom of the same exact element is exactly the same, but that's not actually true, because you could have some elements that, or some atoms of carbon that have a mass of 12, and some atoms of carbon have a mass of 13, and some have a mass of 14. And all of those are different from their number of neutrons. And so that's something you're going to practice with today. You also practiced with your building an atom FET lab. That's when you change the number of neutrons. And what the isotopes did, or the number of neutrons did, is they determined basically the mass number, but they determined the stability of that atom, which is kind of interesting. So let's look at our symbols and how we're going to answer our questions on our practice problems. In this case, we have element symbols, and here you have your symbol, you have your charge here, this is your mass number. So mass number is protons plus neutrons, And here you have your atomic number, and that's what you get from the periodic table. So looking at this example, we have an atomic number of 20, a mass number of 40, and a charge of +2. So protons is 20, neutrons I get from here, 40 minus 20, so top minus bottom gives you neutrons. And electrons, there are 2 additional positive charges than negative charges. So if there are 2 additional positive charges than negative charges, then there are 20 positive charges. There therefore must be 18 negative charges. 20 minus 18 gives you that +2 charge. So in this case, when we're writing isotopes, we can write it like this, where we have the atomic number, the mass number, and the charge. Or we can write it like this, where we write the whole name. This is the isotope name. This is the isotope symbol right here. So the isotope name, you write the name out, dash the mass number. So you could have calcium-39, calcium-41. Another example that you would see is like carbon-12 and carbon-13. You maybe have heard of that in carbon dating. So again, looking at that isotope symbol or that element symbol, we have 8035 bromine -1. So I would write that as bromine-80. This is showing me that I have 35 protons. Then I have a mass number of 80. So 80 minus 35 is going to end up giving me 45 neutrons. And Br is the element symbol. -1 is the ionic charge. So if I take my ionic charge, I know I have 35 positives and I have an overall negative. So I must have one extra negative, which means I have 36 electrons. Again, looking at another example here. So I really want you to take a look at these examples. I have 2 protons. I have 4 is my mass number. So my neutrons is 4 minus 2 is 2. And then here, notice this, I have a +2 charge and I have 2 protons. So if I have 2 extra positives, that means I have no electrons. And I would write this as helium-4. In this case, I have 12, 24, so 12 protons. 24 minus 12 is 12 neutrons. And then I have 2 extra positives, so that means I have 10 electrons. And I would write that as magnesium-24. So you go ahead and try. Give me the answers for protons, neutrons, and electrons, and the name for this one right here. And then for this one right here, I want you to give me protons, neutrons, and electrons. But also note that the charge is 0, so meaning it's a neutral atom. Some review of some vocabulary. An atom is the smallest part of an element that's going to retain the chemical properties. An ion is an atom that's going to carry a positive or a negative charge, and the ion is due to having more or less electrons, because electrons are transferable, and so therefore you can have an overall positive charge or an overall negative charge. I've either lost electrons to give me an overall positive charge, or I've gained electrons to give me an overall negative charge. Isotopes are atoms with a different number of neutrons and therefore a different mass number. And then AMU is the atomic mass unit. It's the mass given to one individual atom based on the number of protons plus the number of neutrons. And our very last slide is groups versus periods. So in your activity today, you're also going to have to identify the group numbers and the period numbers. So the groups, this is a review from Tuesday this week, but groups are going to be your columns, and you can number them all the way across. If you have the link to the periodic table, you want to go ahead and see that. And then another way to number those is we usually have the A groups and the B groups. The B groups are the ones that are lower. You can number them either way, and I will take either answer. And then your periods are your rows. So you start at hydrogen, that's row 1, and then you go down to lithium, that's going to be row 2, and then going down is going to be row 3, and so on and so forth. And then phosphorus, if you looked at phosphorus is 15 columns across, And if you look at the raised columns, it's the fifth raised column across from left to right, and it's in period 3 because you go from the top to the bottom. It's in row 3, so period 3. You're going to need this information for your practice problems. And then finally, I'd like for you to reflect on today's activity. And the reason I'd like for you to do this is, number one, I know that it took a lot of time, and that's probably what you didn't like, and that's fine. But it's a lot of work. I mean, this is what we would be doing in school. But what did you like? And the biggest thing is, what was easy and what was harder, what was difficult? Because I've been going through these for the last Peardeck that I did with this question, and I've kind of gauged how you guys are feeling about different things. So if you could fill that in for me, I'd really appreciate it. And if you have any questions, go ahead and reach out either through tutorial or through email or through Zoom.